So, this lesson we are going to be talking about the Earth's interior. This should be a little bit of review, but I'll give you enough information for the quiz. All right, so um, exploring inside of Earth. Um, so, how we know what the inside of the Earth looks like or how it acts, I guess, what's inside of the Earth, um, is mainly from seismic waves here. Um, we can dig a little bit and figure out like what kind of minerals are inside of rocks, and that gives us a little bit of an idea of how long ago they formed, like what kind of minerals were under the surface, like in the mantle, if it was a metamorphic rock, an igneous rock, or a sedimentary rock. Other than that, digging doesn't really do much to get inside of the earth because we can't dig that far, so we don't really know. So those rock samples, those are going to be evidence, like basically of how long ago those rocks were formed, that type of thing. The real evidence of what the inside of the earth looks like and acts like is from seismic waves. So we have primary waves, secondary waves, and surface waves. Primary waves are going to be those red lines here, and they are, this is important, so write this down. Primary waves are special in that, first off, they're the first waves to be recorded after an earthquake, but secondly, they can travel through solids and liquids. So, right here, the outer core of the Earth is liquid. The asthenosphere here kind of acts like a liquid, but it's not quite one. So we can get a primary wave that starts here on one side of the Earth that we can actually record on the complete other side of the Earth. Then we have secondary waves, which can only go through solids. So here, as indicated in those blue lines, they hit this liquid outer core and then they're unable to go any further. And then there are L waves or surface waves. We'll talk about that a little more when we get into earthquakes. All you need to know is that they travel on the surface of the Earth. Um, so they're able to look at the energies of primary waves and notice that they are able to go to a certain point and their curvature changes a little bit, their energy changes. So right here, it hits this liquid outer core and then it kind of bends. Um, so they're able to tell that that's a liquid area because of this bending. Um, you can see it bends here. It hits that solid core, it straightens up a little bit, and then it bends again once it gets to that liquid core because these seismic waves kind of act in the same way as light. So when light hits water, it kind of refracts. And so that's how they're able to tell the liquidity of the inside of the Earth. um, all right, so main thing we need to know from this slide is that temperature and pressure increase as you go deeper. So like the crust has the least amount of temperature or the lowest numbers of temperature and pressure. And then as you go lower and lower towards the core is the hottest, most pressurized part of the Earth. And temperature and pressure kind of correlate. So with an increase in temperature or with an increase in pressure, you get an increase in temperature, and vice versa. That's just because of the excited states of the particles in that area. So when you have something hotter, those particles move much faster, so they're bouncing around a lot faster. So that increases pressure because there are less spaces inside of that area with more movement. Okay, so the Earth's layers. Again, this should be a little bit of review. We've got the crust, the mantle, the outer core, and the inner core. The mantle is separated by the bottom part of the lithosphere, the asthenosphere, and the lower mantle. And then that outer core is going to be liquid, and the inner core is solid. All right, so the crust, it's made up of hard rocks. It's made up of basalt and granite. So oceanic crust, this is important. Oceanic crust is classified as being high in basalt. And then continental crust is very high in granite. That's going to be important when we talk about plate tectonics. So just remember oceanic crust, basalt, continental crust, granite. And so the crust kind of sits on this layer of the mantle called the asthenosphere. And The asthenosphere is liquid and kind of moves with these convection currents and moves the crust, which is plate tectonics. All right, so let's get into the mantle. So the top part of the mantle is the lower part of the lithosphere. Where that crust sits is the top part of the mantle. And then we have the asthenosphere, which is right here in the upper mantle. It's liquid. It acts as a liquid and has these convection currents. It's where plate tectonics occurs. And then we've got the lower mantle right in here. And so that lower mantle gets a lot of this liquid outer core, hot magma pushing up and creating convection currents. So liquids and gases have convection currents, and essentially what that means is hot rises and cool falls, and it creates this cyclical pattern right here. So we've got this hot magma being pushed up right here and right here and right here. And so those are going to create convection currents. This heat's going to rise. It's going to get to a point where it cools off, it becomes less dense, and then with this rising, it's going to be pushing that more dense fluid to the left in this case. And then as it cools, it's going to fall down, and then it's going to heat back up again right here and create this cyclical pattern of convection. So this is the movement of plate tectonics right here is convection currents. So it pushes up and moves to the left. That leftward movement is where all the crust is sitting on that liquid layer of the asthenosphere. And as it moves left, that crust is going to move left with it. And then you'll get things like subduction zones, but this is due to an oceanic plate colliding with another oceanic plate. And since it's denser, it goes down. Okay, so the core. We've got the outer core, which is composed of, sorry, my dog's barking at me. Outer core, which is composed of liquid iron and nickel. The inner core, which is composed of solid iron and nickel, right there. And the important thing to know about the magnetic field is that it originates in the outer core. So when you think about magnets, you think about like metals, like iron and nickel. They are really good magnetizing metals, and that's just due to their chemical structure. But so since that outer core is very high in liquid iron and nickel, it kind of, as it moves, it changes the Earth's magnetic field. So the magnetic field does reverse through time, and that's just with that movement of the outer core, like percentages of iron and nickel. So there may be like a higher percentage of iron and nickel up here and to the north. So you're going to have a higher area of effect for magnetization going north. So you're going to get this like polarity coming north and south throughout the Earth. Whereas if you had it on this side, the magnetic field might be going around sideways cyclically. So here's going to be just a little, be quiet, just a little graphic here about the magnetic field. So right here, we're going to see these are the poles, so north and south pole here. The magnetization is going to be very, very high at both of these poles, and it's going to create this like little cyclical field of magnetization. And this actually helps with a lot of things like radiation and stuff. So it's pretty interesting. One thing to note is that for that switch, that reverse in magnetization that we talked about in the last slide here, reverses through time. We have evidence of that by looking at the position of rocks. So we can look at old rocks, millions of years old in rock layers that have their poles are they're opposite from what we have today. So say the poles may be charged like pointing upwards today to the North Pole. These rocks that we found up in here may be pointing downwards because that's the way they were deposited and their magnetization pointed them that way. So that's how we can tell that it's been changing throughout time. Other than that, that should be all you need for this unit. And if you have any questions, like always, call, text, message me. Um, I can help you understand most of this stuff. So if you need any more information, go ahead and let me know. Other than that, good luck and have a great week.